So yes, I'm going to talk today about essentially the design and development of a baby tokamak that is the start really of a journey which will hopefully lead to a series of larger tokamaks that will become a power plant, but we'll see, it's early days yet. So, so the challenge, so what we're trying to do. We're trying to create a small, cost-effective tokamak for approximately 300 research centres in the world to use for exploring magnetic compliant fusion. So a tokamak is the device used for magnetic compliant fusion. Using NI CompactRIO hardware and LabVIEW software, develop a powerful data acquisition control system for a small tokamak, providing power physics research centres easier access to the technology they need to accelerate their research with less expense. So, a simple guide to fusion here. I'm not a plasma physicist, I'm a systems engineer, but I'll give a simple guide here for those who don't know. The easiest way of generating fusion power is essentially to fuse deuterium tritium metals together to form, as you see like the demonstration here, helium, an alpha particle and a neutron. Now, in doing so, you actually release a high-energy neutron, 14.1 eV, with a number of gamma rays, generates quite a lot of energy. However, in order to do so, you require a temperature around 150 million Kelvin to actually ensure that you get a reasonable power return. Now, the beauty of fusion, of course, is it's clean, well, relatively clean. It's abundant, deuterium and lithium are easily available. A kilogram of fusion fuel is roughly equivalent to 10 million kilos of oil, 10,000 tons of oil. So it obviously has certain attractions in terms of its efficiency. It's safe, it's relatively safe. There's no long-term radioactive waste, as you do with fission systems. It tends to be more low level, rather like in medical systems. There's no risk of meltdown because the system itself is maintained by a system of magnets and electrical discharge, so as soon as those stop, fusion reactions stop. And it's competitive. Well, we believe it is with the right kind of design. So, maintaining fusion, I said you need 150 million degrees centigrade, roughly 10 atmospheres of pressure as well. Well, it's already been done at the JET experiment in Culham in Oxfordshire, where I'm based, in 1997, using a deuterium tritium fuel. I think it was about 20 seconds actually managed to burn to generate roughly the same kind of energy that they're putting in. But that's a very, very large magnet system, as you can see, and I'll explain exactly what that is in a moment. So, a tokamak, well, at the moment this is the most successful form of fusion device. It comes from the Russian toroidal chamber magnetic coils, and actually the first one was built in 1960. And what we have here, sort of go back, what we have here, essentially is a magnetic, some donuts essentially, with a set of toroidal field cores that squeeze the plasma, and a set of colloidal field cores which stabilize it. So essentially it acts as a magnetic bottle in order to contain the plasma, because if you have a plasma at 150 million degrees centigrade, it's very important it doesn't come into contact with the chamber walls. So while it's being stabilized and held by the magnetic fields, at the same time we're actually using ohmic heating of we're actually using a variety of methods to actually heat the tokamak using radio frequency and neutral ion fields. So we contain it and we heat it. So that's the basis of a simple explanation. What's happening today in scale-up in tokamaks is at the moment ITER, which is the big brother of JET, is being built in the south of France at the moment, and that's aiming to be the world's first truly functioning fusion reactor in terms of reducing break-even, i.e. a lot more energy out than comes in. However, timescales are a bit of an issue here, but ITER will hopefully be running by about 2029. After that, there's another one planned demo, which will be a demonstration power plant, maybe the 2050s. And then before finally we've got some kind of power generation, we're looking at 2075 and beyond. so really towards the end of the century. Those are high-cost projects, really well, lowish risk, but obviously development can be quite slow. It's understandable, they're tremendous feats of engineering. However, there is another possible solution, which is not a replacement, but maybe an adjunct to the larger systems, called the compact spherical Tokamak, which is essentially a design that uses very high magnetic fields in a fairly small device with a relatively spherical symmetry. The idea behind this is, according to current modeling anyway, states that something called we have high beta, which is very high efficiency. That's the ratio of plasma pressure to magnetic pressure. And when you have a large value for that, the theory seems to state that you'll be able to get very high efficiency out of the device, even for a relatively small device. At the moment, the large devices might have a beta of just a few percent. This design is over 40%, so potentially it's over 10 times more efficient. So we combined this small compact design with another new development, which is high temperature superconductors. In 1985, those discovered fairly recently. But when you cool those down below liquid nitrogen temperatures, down to say 20 or 30 K, you can actually get very high magnetic efficiency from them. Plus the fact they're actually quite neutral, supposed to be quite neutral hardy. So a combination using high temperature superconductors and a spherical Tokamak produces potentially quite an interesting device. And recent results from modelling on NSDX and mass devices suggest that spherical Tokamaks may have a significantly higher confinement, a high magnetic field of 3 Tesla. In other words, they work much more efficiently as a magnetic bottle in the way that they can heat and contain that plasma. As I said, we're aiming for around 150 million degrees C and over 10 atmospheres of pressure in order to produce a break-even device. So taken together, the idea is that maybe a device maybe 10 to 50 times smaller than ITER could have a very high gain, though a relatively modest fusion output. But because they're quite compact, you could actually operate a farm of these as opposed to one large massive device. You have several of them running together to use a power plant. So what have we been doing? Well, we've been building some small experimental devices just to test out the concept, really. The first one, the SD25 copper, was operational. We got operational about 18 months ago. I should say that using LabVIEW as our control system, as well as distributed CRIO and various other things, we managed to get the whole thing together in 3 to 4 months and operating, producing a plasma. Now, that's only a baby device, it's around 0.1 Tesla, but it's quite interesting and useful for demonstrating some of the plasma physics concepts. Just last week, we got operational our fully high-temperature superconducting version, which has, we believe, the most complex HTS magnet assemblies ever produced. And that's why it took us 18 months to sort of get as far as we have, which can produce, using superconducting magnets, we can produce very, very long burns. At the moment, we've managed to get a 7-second plasma out of it last week. But we're aiming for minutes and hours, even longer. I'll talk about that more towards the end. So the SD25, as I said, it's a baby Tokamak. So to power the magnets, we had a battery of 8 1-farad capacitors, which is switched by IGBTs, which are insulation gated by polar transistors. All of this is triggered by LabVIEW, of course. High voltage capacitor banks discharged through a solenoid coil that goes from the central device and coupled essentially electrical energy to the plasma. Cheapest toroidal field about 0.2 Tesla per second. Plasma current of around 10 kiloamps. On top of that, we're injecting hydrogen gas into the chamber using piezoelectric actuators. Again, CRIO control. We're pulsing a 3 kilowatt or 3 to 5 kilowatt magnetron to generate heating of the plasma. We have high-speed video for the to actually look at the cameras, look at the plasma, and spectrometers and plasma diagnostics. Again, all integrated under LabVIEW. So a quick system overview, and essentially the blue boxes show parts which are implemented using National Instruments hardware. But essentially we had a main LabVIEW application, which is running using network variables and NI beta over the Ethernet, and the actual control systems are individual CRIOs. So each CompactRIO combining FPGA and RT was, for instance, responsible for triggering the capacitor banks as far as magnets and generating magnetic fields. Another CompactRIO is responsible for digitizing from various sensors and optical sensors around the chamber to do data acquisition. We also had a vision server based on NI iMac, which we were using for a high-speed camera system. So again, the beauty of all of this is it all networks together very nicely using LabVIEW and such. And it's quite a complex system, but again, that really helps a lot. So just looking at the control system on this, in the first version, 2 CompactRIOs run the system. And so a plasma discharge control, capacitor discharge current waveform monitoring. That's the one just up here on the left-hand side. Data acquisition, so plasma diagnostics, sensors and voltage loops. We had to trigger and synchronize multiple I/O channels with microsecond resolution at millivolt and even microvolt sensitivity. So we're using NI 9205 16-bit modules, use a lot of those in fact. NI 9477 digital out, 9253 D2As for modulating power supplies, and 9215 100 kHz data feed modules. But again, there are lots of new modules coming out, and our new systems are using really what becomes available as it becomes available. That's again the beauty of our fast development approach. Using LabVIEW FPGA, so FPGA code for real-time data acquisition and trigger generation, using the DMA FIFO, real-time loops and shared variables to create a powerful networked architecture that can be easily scaled in size and complexity. The key in size and complexity is that actually on paper, our control system is actually quite similar to the architecture that will be applied on ITER 1433 frame grabber, which is a dual camera link, a very high bandwidth frame grabber to collect high-speed data of the video of the plasma at over 1,000 frames per second. And we're using a little Fazda race camera to do that. And then again, using an iMac drivers to allow the acquisition to be easy configurable, to allow for easy conversion of the video files to API. So using this kind of setup for just a few $1,000s, we have multiple channels of very high-speed video, basically sitting around the chamber looking at plasma. And again, the beauty of that again is that if we want the next generation, we can stream all of those channels of video into an RT target and then start processing them to do real-time plasma control as well. So that's all under our control. So hopefully I can show you plasma discharge with a click of the mouse. Let's see what I can show you. So, right, so I can Anyway, sorry about that. No plasma, but you can come and see me later if you want to see a whole variety of plasma videos showing what actually happens in the chamber. I mean, just to show you stills what we're actually seeing there on the image is just to the right-hand side. You can see those little arcs, which are essentially the plasma surface, this is not a fully functioning Tokamak plasma yet, but it's starting to form in the sense that once it's there, you can actually see a closed surface of plasma within the chamber. It's just starting to form, as you can see those images. But as I said, I've got it on the laptop, so if anyone's interested, I can show you. So control interface, so sitting back at the PC side, again, a very feature-rich, useful GUI for setting everything up, lots of parameters in terms of power supplies and gas injection, microwave, all of that handled from a LabVIEW front end. And a key thing here as well is that a single Ethernet cable connects the Tokamak control system to a master PC running LabVIEW. So just a single Ethernet cable between our control PC and the entire Tokamak system. So using shared variables, NIVs, this networks all the components, and we can see all those high-speed data video capture, spectrometers, power supplies, all together. The SD25 is then contained within the Faraday cage and controlled from safe group. And that's an architecture that we continue to extend. It's obviously the concept of one of these devices is that you can remotely operate it quite easily. So the control system actually sits within the hot area, you might say, whereas the controller sits way back, which is network, sits way back in a safe area. Right, I mentioned earlier about superconducting Tokamak, which is really obviously it's a build a power plant, you've got to have superconductors because that way they will run continuously. What we've built here is, well, just a quick explanation. So high temperature superconducting magnets can induce high magnetic fields and create protoplasmas for a longer period of time. One of the problems with high temperature superconductors is their ability, well, the way that they quench, i.e. that's when they turn from the superconducting state to the conducting state. Essentially, you've got hundreds of amps flowing through those magnets, which then through resistive losses will heat the whole thing up and damage the tape. So to that end, we have a quench monitoring system based upon the latest 9068 and the 9076 CRIOs and a whole battery of 9258D modules. And I think this is a project in itself, really, because we're monitoring over 100 channels to microvolt resolution at several kilohertz. And ultimately, it's early days yet, but we tend to do a variety of adaptive processing on that to help us control the magnet. But you see on the right-hand side there, you see the actual assembly that before it goes into a cryostat. You can just see that slightly yellow-coloured, brass-coloured rings. That's actually the tape. There are about 120 meters of tape per coil, and there are 6 TX coils and 4 colloidal coils. Just quickly, in terms of the architecture of it, it's a lot more complex than the copper one in the sense that we've got several CRIOs here. One that controls discharge, gas, microwaves, a high-speed vision server, an RT, a real-time controller for plasma control, and various quench detection systems. I'll talk about the RT Rio essentially uses MXIE to a quad-core Xeon real-time target. We haven't commissioned this yet, but essentially the idea is that we can stream in information from various sensors and optical and cameras and use that to stabilize the plasma. So I talked about keeping the plasma stable within the chamber, particularly over long burns is very, very important. Where are we going at the moment? Well, the first results were November 2013 for just the colloidal field magnets. And actually last week, we managed to achieve full operation of the whole superconductor system. We managed to run for about 7 seconds. And actually this week we're in hopefully a bit longer. As you can see, I mean, HTS promises much better magnet performance. The standard superconductors running full below 50K. And real-time plasma control and monitoring, as I mentioned, using RT time, NI CompactRIO. Just looking at just the cascade of images down there, what you see at the top there are liquid helium tubers that are essentially feeding the magnets. Obviously, in order to get the low temperature, we're just sharp using conditioning the chamber walls, but anyway, it just gives you some idea what it's like. Moving rapidly on, where next? I mean, we've just got this running, and being a fully privately funded company, it's important to have results like that to get our next rounds of investment. And thankfully, we've got our next round of investment to build this, which is an ST40, which is going to be the real deal in the sense that it's going to prove, hopefully, the theory of confinement that we can use the design of the high field intuitively test labs to verify energy confinement scaling in a high field spherical tokamak. This device will have copper magnets and possibly some high temperature superconductors. But at the moment, that technology requires more development to get to these fields. But the key here is that if we can achieve these 2 to 3 Tesla fields in this small device, with the aim of this device is that we'll actually reach fusion temperatures, not generate fusion, but show that the plasma can actually reach fusion temperatures. And this will feature advanced supercapacitor-based power supplies and liquid nitrogen cooling with copper. In parallel, we'll be working on a high-field, high-temperature superconducting magnet, because we really believe that HTS magnets are a real key to the advance of fusion power. And if we can get that solved, things will be a lot much faster. And I said from that, hopefully, onwards to the fusion pilot plant based on these advances. But again, there are enormous engineering and technical challenges here. In fact, I noticed there were around 3 papers on the poster there talking about various aspects that are very important to tokamak development, quench monitoring of magnets, lithium injection, and various spectroscopy, microwave diagnostics, all very important. So they're tremendously complex systems. But the beauty of building small ones is that hopefully you can speed up the development cycle. Just finally, just to finalise where we are. So magnet technology, this is a real key here, is rapidly improving, allowing higher field designs using next generation superconducting cable. A high field device, 3 Tesla, the SD40, is already under design and will start construction hopefully early 2015. All of that will require the set real-time plasma control, adaptive microwave, enhanced diagnostics, improved quench detection, a lot of control subsystems, which are going to very much be more applications for LabVIEW RT, CRIO, FPGA, and everything else.